Hello everyone. So today's session we will discuss about the relation between elastic constants. So we all know for a given material the Young's modulus, bulk modulus, modulus of rigidity and Poisson's ratio are constants. So now we will find out what are the relation between these four constants. First we consider the Young's modulus and Young's modulus, bulk modulus and the Poisson's ratio. Relation between Young's modulus, bulk modulus and the Poisson's ratio. So for that let us consider a cube whose sides each of length L are parallel to three coordinate axes X, Y and Z. Let a uniform normal stress P be applied over its surface. Then each side of the cube is under an external stress P. That you can see here, each coordinate axis is having we are applying a uniform normal stress P applied over entire surface. Then you can see the normal stress is parallel to each axis. Okay, the stress P acting parallel to x-axis will produce, so here you can see the x-axis, the P is parallel to x-axis, will produce an extension parallel to x-axis and compression parallel to y and z axis. Okay, so and if the extension is parallel to y axis, what will happen? Yeah, extension is acting to y axis, then z and x axis you can see there is some compression. If the pressure is applying parallel to z axis, then the extension is parallel to z axis and you can see there is compression along y and x axis. Okay, so now we will calculate the Young's modulus. So already you know Young's modulus will be y. Young's modulus is stress by strain. So here the stress we can write it as F by A and it is divided by strain, that will be L by L, change in length by original length, and you can write it as L by L. Okay, or we can write P L by L. This is equation number 1. So where L is the extension produced along x-axis. So you can see here the stress P acting parallel. So I am first considering the first case. The stress P acting parallel to x-axis will produce extension parallel to x-axis and compressions parallel to y-axis. Okay, so stress, that I will write it here, stress P along x-axis. Okay, that is the case we are discussing here. Then extension is along x-axis and compression along y and z axis. Okay, so this is the first case. And we got the equation for we have to find the equation for L. So L will be L equal to, from this equation we can write PL divided by Y. So this is equation number 2. And next we have to find out the value for compression. Compression parallel to y-axis. Parallel to y-axis is given by, for that we have to find the compression is happening there. So we have to find the lateral strain there. So lateral strain, this one will be equal to lateral strain into initial length. So lateral strain will obtain by, from the equation, Poisson's ratio. Already you studied Poisson's ratio is the ratio of lateral strain to longitudinal strain. So lateral strain will be Poisson's ratio into longitudinal strain into initial length. This is the equation. So we can write it as Poisson's ratio denoted by the letter sigma and longitudinal strain into initial length. We can write PL divided by Y. Okay. This is the equation for compression parallel to y-axis. This is the same equation we will get for z-axis, compression parallel to z-axis. So compression parallel to z-axis is written by the equation sigma P L divided by Y. In the same way, the stress parallel to y-axis will cause extension parallel to y-axis and compression parallel to x-axis and z-axis. So now we will consider the same thing. The stress parallel to y-axis will cause extension parallel to y-axis and compression parallel to x-axis and z-axis. Okay, so the same equation we will get here also. The stress parallel to y-axis will cause extension parallel to y-axis. Will get an equation. The extension produced parallel to y-axis is the same equation that we got in here, the same equation. So that will be PL divided by Y. So this is the equation. And here I will write it as equation number 3, and here it is 4, and this one here equation 5, and the compression parallel to x and z axis will be sigma PL divided by y. This is equation number 6. And in the same way, the third case will also we will get third case, the stress parallel to z axis will cause extension parallel to z axis and compression parallel to y and x and y axis. Okay, so the equation will get here, extension produced parallel to z axis will be PL y divided by y, that is equation number 7, and the compression parallel to x and y axis equal to sigma PL divided by y, that is equation number 8. So we get same type of equation here, and we have to find the net extension parallel to 3 axis. So for that, net extension parallel to the 3 axis is given by PL divided by y, that is the extension happening here, and we will get 2 compression here. So compression 2 times will come and it will just opposite sign. So when we add this become extension will become positive value, and the other terms will come as sigma PL divided by y, that is one compression, and another compression also will come another direction. So PL divided by y. Okay, so it is in the opposite direction, that's why we are when we adding when we find the net value we will put negative sign here. Okay, and the equation will become PL will be the common term, so I am taking outside PL divided by y, 1 minus 2 sigma. This is the term. Then so this is the extension parallel to 3 axis that we got here. So when the cube is in the original position, we have the original length L, and the extension now added this much value. Okay, so we can say thus each side of the cube having L length. Okay, so each side of the cube increases from L to L plus PL divided by y, 1 minus 2 sigma, this much value. Okay, so next we will find out the new volume of the cube using this extension value. Hence the new volume of the cube equal to L plus PL divided by y, 1 minus 2 sigma all cube. So we know the cube can be found by length cube, L cube. So this is the new volume of the cube. And for solving this, we can write it as L cube plus L cube. Here we can, okay, L cube and this term cube will come. Okay, L is common here, so I am taking outside. So L cube 1 plus P divided by Y 1 minus 2 sigma. So this one will be all cube. So using binomial theorem and neglecting the higher powers, we can reduce the term as higher powers of 1 plus P divided by Y. Okay, higher powers of P divided by Y 1 minus 2 sigma. We can write this as L cube, and this one will come as 1 plus 3P divided by Y 1 minus 2 sigma. This is the term that we get. Okay. Hence, next we find out the change in volume. Hence, the change in volume will get by small v equal to L cube 1 plus 3P divided by Y 1 minus 2 sigma all bracket minus L cube. Okay, so this term will be the change in volume. L cube is the original volume. So change in volume we will get by the new volume minus the original volume. We will get the change in volume here. Okay, so we will be L cube will cancel. We will get 3P divided by Y L cube 1 minus 2 sigma. This is the term. Therefore, volume strain will be equal to V divided by capital V. We get V divided by L cube. It will be L cube by L cube 3P divided by Y 1 minus 2 sigma. This is the term, and we will get it as 3P divided by Y 1 minus 2 sigma. Okay, and the volume strain is dependent with the value bulk modulus, so we can apply the equation for bulk modulus here using the stress P. So we can write bulk modulus K will be equal to P V divided by V. So from this equation, volume strain means V divided by V is volume strain. Okay, so we can apply the value here. So we will get the equation Y divided by 3 into 1 minus 2 sigma. Other terms will cancel out. Now we can write Y in terms of K will be like this. Y equal to 3K 1 minus 2 sigma. This is the one equation that we get. Okay, so this is equation number 9. Okay. Equation number 9. So now we get one relation between y, k and sigma. Next we will find the relation between y, that is Young's modulus, rigidity modulus and sigma. So for that I will just write here relation between y, rigidity modulus and sigma. Okay, so for that let us consider a cube of side length L upon which an extension stress P parallel to y-axis. So this is the extension stress P parallel to y-axis, and a compressional stress that you can see here, the arrow is going down, so that is a compressional stress P parallel to x-axis is applied. So there is no stress parallel to x-axis. Okay, so let us consider a cube of side L upon which an extensional stress P parallel to y-axis and a compressional stress P parallel to z-axis is applied. Point that there is no stress in the direction of x-axis. There is no stress parallel to x-axis. Okay, so now we find the extensional stress P produces extension along y-axis. So that we will get by the equation PL divided by y. Okay, so compression along z-axis will get compression along y-axis, and z-axis will get by the equation. So z-axis will get along z-axis is equal to sigma PL divided by y. Okay. Similarly, the compressional stress P produces compression along z-axis PL divided by and extension along y-axis and x-axis. The same thing will happen. Thus we can find out the net extension along y-axis, which will be equal to PL divided by y plus sigma PL divided by y. So this will be equal to PL divided by y 1 plus sigma. So this is equation number, this is 10 and this is 11 and this is equation number 12. So now we get the next extension along y-axis. Since there are equal extension and compression along x-axis, we can write x-axis as there is no change along x-axis. Each side of the cube is initially of length L. The extension and compression strains along y and z axis respectively are each equal to. So now we can write the extension and compression strains along y and z axis respectively are each equal to PL 1 plus sigma divided by y into L. So the equation will be P by y 1 plus sigma. But we know this is the case of a shearing strain, okay, that we are applying the force only on the one direction is free there, okay. So only there is no change along the x-axis, and compression and extension is acting only on y and z axis. So now we can find out the shear angle theta. So the angle shear angle theta will be shear angle theta will obtain by what is that? Yeah, it will be the extensional longitudinal strain. It will be equal to longitudinal strain. So we can write it as this is the longitudinal strain L by L. So we will get the value as P divided by pi 1 plus sigma, and plus, so the shear stress is actually simultaneously equal to extension and compression strains at right angles to each other, so equivalent to a shear theta. Then we can say that it will be this is the case of one extension and compression. So we can consider if the y-axis is in parallel to extension and z is parallel to compression, then we can consider only one term here, that is one term, okay. If z-axis is having extension, then y-axis will having compression, okay. X-axis will there is no change in x-axis, so shear angle will come will be get by taking the net component, okay. So net component will be, this one will come it as 2 times, so P divided by y 1 plus sigma and P divided by y 1 plus sigma. This is the equation, and we will add these two, we will get 2P divided by y 1 plus sigma, that is theta. Now we already know what is modulus of rigidity. Rigidity modulus will be equal to N equal to F divided by A, that is stress by strain itself. Of course here the shearing strain will be theta, F by A theta, and we can write it as P by theta. So it will be, from this equation, P by theta will be equal to y divided by 2 1 plus sigma. This is the equation, and we can also write the term as N equal to okay, y equal to 2n 1 plus sigma. This is the equation. This is the final equation that we can write by connecting, okay, 13, equation number 13, okay, Young's modulus, rigidity modulus and sigma, okay. Next we can find out the relation between okay, that I will write on the next page. So relation between y, k and n that we obtained from the last two equations that we already got, the relation between yk and sigma and yn and sigma. From that equation we can find out the equation for yk and n. So we have y equal to 3k 1 minus 2 sigma, and another equation we find y equal to 2n 1 plus sigma. So from this equation, this is equation number 1 and this is equation number 2. From equation 1 we can write 2 plus 2 sigma equal to, okay, just a minute. From equation 1 we can write, just rearrange the equation 1, we can write 1 minus 2 sigma equal to y divided by 3k. This is equation number 3. And from equation 2, we can write 1 plus sigma equal to y divided by 2n. And we can multiply this with the 2. We can write it as 2 plus 2 sigma equal to y by n. So this is equation number 4. Now we can add equation, adding equation 3 and 4. What we get? Yeah, 3 equal to y by 3k plus y by n. That means 3 divided by y equal to 1 divided by n plus 1 divided by 3k. This is the relation between y, k and n. This is equation number 5. Next, the relation between k, n and sigma. For that we can write y equal to 3k 1 minus 2 sigma, that will be equal to 3k minus 6k sigma. Then y equal to another equation is 2n 1 plus sigma, which will be equal to 2n sigma. Equating these two equations, we can write 3k minus 6k sigma equal to 2n plus 2n sigma, which will be, we can make the sigma terms to one side. So 3k minus 2n will be equal to sigma, okay, 2n sigma plus 6k sigma, and we can write it as sigma 2n plus 6k, okay, and it will be sigma equal to 3k minus 2n divided by 6. Okay, and just rearrange this time, 6k plus 2n. Okay, this is the final one. So and now we got all the relation between y k sigma, y n sigma, k n sigma, and y k and n. 4 main equations that we got from this relation. The mainly the questions asked from the sessions based on the they have to derive the relation between elastic constants. Otherwise they will ask some problems based on this session.